In this video I will tell you about our work on neural radiance field learning with outposed camera. NeRF and its follow-ups achieve an unprecedented level of fidelity on a range of challenging scenes, but most of these methods rely heavily on knowing the accurate camera poses. Recently, several methods attempt to reduce dependence on pre-computed camera poses, but still require specific conditions. To this end, we introduce GNeRF. Our algorithm has two phases. The first phase gets coarse camera poses and radiance fields with adversarial training. The second phase refines them jointly with a photometric loss. We use adversarial learning to predict a rough pose for each image and also learn the rough radiance field of the scene. We get the real patch from the dataset and generate fake patch by the generator G. Taking a random camera pose as input, the generator G will synthesize the image observed at the view by querying the neural radiance field and performing NeRF-like volume rendering. The set of synthesized images from many sampled camera poses will be decomposed into patches and compared against the set of real patches by the discriminator D. Along with the two standard components, we train an inversion network that maps image patches to the corresponding camera poses. After the pose-free NeRF estimation step, we obtain an initial NeRF model and camera pose estimates for the training images. In Phase B, we refine the pose embedding in the NeRF model by minimizing the photometric reconstruction error. To further mitigate overcome local minima, we propose a regularized learning strategy by interleaving Phase A and the Phase B to further improve the quality of the NeRF model and pose estimation. Here, we show novel view RGB image and depth image of our method on 6 scenes from the synthetic NeRF dataset and on 3 scenes from the DTU dataset. The novel estimation strategy based on an integration of adversarial training and an inversion network enables our methods to optimize camera poses with large trajectories and random initialization. The refinement step with photometric loss further improves the accuracy of the camera pose and radiance field. Our full architecture of the combination of adversarial training, inversion network, and photometric loss gets the best accurate camera poses. Without either the adversarial loss or the inversion network, the model is incapable to learn reasonable camera pose initialization. Without the photometric loss, the model is only capable to get rough camera poses. The iterative optimization scheme gets much finer geometry along the edge, and the estimated camera poses align much closer to the ground truth camera poses. Our method can even estimate camera poses and neural radiance fields jointly when the input views are only textureless gray masks. This case further demonstrates that our architecture can estimate camera poses from high-level features of an image without reliance on key points or textures. Finally, we test our method by adding intense noise to the training images. Surprisingly, our method is not sensitive to the noise and still able to render novel view images. Thank you for watching.